Hello, sir. I'm Balaganesh, and today I'll be giving my video presentation on the topic of audio signal processing. So what are we going to talk about in this presentation? First, I'm going to talk about audio filtering, and then I will talk about pitch shifting of audio signals to important techniques in audio signal processing. First, I'll talk about audio filtering. So what is an audio filter? An audio filter is used to alter the frequency contents of an audio signal. More precisely, it can attenuate or in some cases even amplify certain frequencies present in a signal. Another use of audio filters is to isolate certain frequencies of a sound in order to boost them, that is, amplify them or make them more prominent. There are four basic types of audio filters: low pass, high pass, band pass, and band stop. So a low pass filter is a filter that passes all the frequencies below a specified cutoff frequency and attenuates all others. A high pass filter, as you can see, is exactly the opposite. It attenuates frequencies below the cutoff and passes frequencies above it. A band pass filter allows frequencies only in a certain range or band to pass through the filter, and all the others are attenuated. A band stop filter is just the opposite, which allows all frequencies to pass except for the frequencies in a specified band. Normally, filters are characterized by their transfer function, which is nothing but the impulse response of the filter in the frequency domain. Remember that an impulse contains sinusoids of all possible frequencies, and hence the transfer function will describe how each frequency component in a signal will be affected. So from the transfer function of a filter, you can determine its magnitude and phase response. Magnitude response is what you get when you take the magnitude of the transfer function, and it describes how each frequency component is attenuated or amplified. And the phase response is, as the name suggests, describes how each component of the signal is phase shifted. Also, sometimes the magnitude response is plotted on a decibel scale, which I will describe shortly. So let us look at some filter parameters. I have described the filter parameters for a low pass filter, but generally all the types of filters will have similar kinds of parameters. The most important ones are the passband and the stopband frequency. Passband frequency in the case of a low pass filter, denoted by omega p in the diagram here, is the filter below which all the frequencies ideally will pass through the filter. And the stop band frequency, on the other hand, for a low pass filter, denoted by omega s in the diagram, is the frequency above which all frequencies are attenuated, that is, in an ideal filter. Stop band attenuation of a filter measured in decibels is the extent to which the frequencies above the cutoff are attenuated, and the decibel scale is defined as follows: dB is equal to 20 times log of AI by AO by AI to the base 10, where AI and AO are the input and output amplitudes of the signal respectively. Now let us look at some other filter parameters. The passband ripple is the maximum fluctuation in the magnitude response of the filter in the passband region. You can see here from this figure that the magnitude response of the filter is fluctuating in this region, and in decibels we measure it as minus 20 log to the base 10 of 1 minus delta 1, where delta 1 is shown here in the figure. And a stop band ripple is a similar measure in the stop band. Is the maximum fluctuation in the magnitude response in the stop band, given as minus 20 log to the base 10 of delta 2. So typically in digital filters with a finite impulse response, you will have these parameters as finite, because no filter is ideal. There will generally be some ripple over here and over here. And also, as I mentioned earlier, other kinds of filters will have similar parameters. How do you choose the parameters of your filter? So one thing you can do is take the Fourier transform of the given audio signal, and so that you get the frequency spectrum, and accordingly you can try and decide which frequency components you want to attenuate. Usually the noise will have a very high frequency in the signal. Accordingly, you can decide values for the different parameters of the filter, as I have discussed. It also helps to visualize the filter's frequency response as well as the spectrum of the signal after you filter it. And last but not the least, make sure you listen to the filtered signal as well to make sure you have achieved the desired purpose. Here's an example of filtering I did with an audio clip I recorded. The plot on the left shows the magnitude of the Fourier transform of the signal before filtering, and the plot on the right shows the magnitude of the Fourier transform after filtering the signal. So you can see over here that the filter is a low-pass filter, so you can see over here that many of the high-frequency components present in this signal are not present in this signal. So how do these audio clips sound? Let's listen to the one before filtering.
Hello, this is a test.
And the one after filtering sounds like this.
Hello, this is a test.
So you can easily make out that some of the all the high frequency noise has been removed after filtering the sound, but you can also notice that the quality of the sound has gone somewhat down. So this can be overcome by using different audio signal processing techniques. Anyway, the filter that I have used is a low-pass finite impulse response filter with the following specifications as shown here. The passband frequency of the filter was 570 Hertz, and the stop band frequency was 2000 Hertz. And also the passband ripple was set to 1 decibel and the stop band ripple to 80 decibels. So you can the magnitude response of the filter with the y-axis on a decibel scale is plotted over here. So you can see that the lower frequency components are allowed to pass and the higher frequency components are effectively blocked by the filter, as you can see. So now let's look at some applications of filters. Low pass filters are used to remove high frequency noise and isolate bass from a recording. High pass filters are used to remove bass lines from a music file or some other low frequency content. Band pass filter is typically used to isolate a specific band of frequencies for boosting them or amplifying them. And band stop filters can be used to remove certain bands of frequencies that may be problematic in your audio file, such as mic feedback. This completes our discussion on audio filters. Now let us look at pitch shifting of audio signals. What is pitch shifting, first of all? Pitch shifting basically refers to multiplying the frequencies of all the sinusoids of a signal by a constant. So in music, the extent of pitch shifting is measured in semitones, where one semitone corresponds to multiplying by a factor of 2 to the power 1 by 12. The choice of this definition is associated with the relationship between the frequencies of well-known musical notes. And also, pitch shifting need not be applied to only a musical clip. It can be applied to any audio clip. So the most intuitive way of pitch shifting of signal is by time scaling it or resampling it in the case of discrete signals. While this does indeed alter the pitch, the issue is that it changes the duration of the signal also by the same amount. Recall that when you time scale a signal, it will get compressed or stretched, so the duration gets changed. So how do you change the pitch of an audio signal without affecting its duration? For this, we can solve the related problem: how to change the duration of an audio signal without affecting its pitch. There are several techniques to time stretch an audio clip in this manner. One technique is called overlap and add, or OLA. And it is a very basic algorithm for this purpose. First step is to create equally spaced overlapping windows of the signal. And by windowing, we mean multiplying the signal by some function such as a Gaussian function centered at a specific time. And we make several such windows by multiplying by different Gaussian functions centered at different time points. Then we change the spacing of the windows by the specified amount, the extent to which you want to time stretch the signal, and then you combine the windows back. While this does do well in recreating the magnitude spectrum, this can, however, introduce phase jumps in between the windows, meaning that when the new audio signal is played, you might get some random noise in the middle corresponding to the phase jumps. A modified technique, which I'm going to just discuss briefly here, is the waveform similarity overlap and add technique. It's just basically a modification of OLA, which tries to smooth out the phase jumps. It's an iterative method which in each iteration searches a certain number of samples around the windowing interval for a window that minimizes phase jumps. So it's basically a modification of the previous technique. And in fact, it gives better results than simple overlap and add. Apart from this, there are many other techniques to time stretch a signal as well. After you time stretch, then what you can do is resample the signal and bring the time duration back to its original value. And of course, in the process, the pitch of the signal will get changed as well by the specified amount. So in the case of, if you want to compress this signal, then you need to undersample it. So, and if you want to stretch the signal, you'll need to oversample the signal. And since the signal is discrete, you might need to make estimates of the signal at some intermediate points by using interpolation or some other technique. And the result is that the signal is changed in pitch, but not in duration. So that is how pitch shifting is accomplished. Now, here is an example of pitch shifting I did on another audio clip I had recorded. So MATLAB has an inbuilt function in its audio toolbox, which pitch shifts a sound by a specified amount in semitones. The plot on the left shows the frequency spectrum of the original signal, and the plot on the right shows the frequency spectrum of the pitch shifted signal. That is, I pitch shifted it by -5 semitones. So you can see that the peak frequency on the left in the left plot is higher than the peak frequency in the right plot, showing that the pitch shifting was done successfully. Let's listen to the original audio clip first.
Hello, this is a test.
So that was the original audio clip. Now let's listen to the pitch shifted one.
Hello, this is a test.
Wow, well, that is a dramatic change, isn't it? Because of the pitch shifting, the entire tone of the voice has been changed. So that, in fact, is one of the main applications of pitch shifting. You can change the tone of a person's voice and make it similar to that of a different person. Of course, pitch shifting is extremely useful in music production as well, and it can be used to change the pitch of an audio clip so that you can use it in another song you're trying to produce. So yeah, with that, we come to the end of the discussion on pitch shifting. Here are some of the references I used when making this presentation. Thank you, sir.